First we have to choose a type to begin with. And there are so many possibilities, I will simply be guided by parsimony when I don't have a better criterion. So let's try the event level at type 6, which is far more than you need by ordinary estimates for physics. But type 5 is much too small. And associate the monadic, the first grade elements of Q with fermions, therefore. The picture I drew, the table, is not truly informative about the nature of these symbols. They all have a certain height and a certain width, and they look roughly square. In fact, if you look at any type like 6, the vast majority of the symbols are over 10 to the 1,000th power long, but only 6 high. So they're longer and skinnier than DNA molecules. But the fact that they're almost linear makes the problem of encoding the universe in them a little bit like in the problem of decoding DNA, but it's in the opposite direction. We have to encode rather than decode. Of course, optimistically, we hope that we are really reading a code that exists already. But that's perhaps being too hopeful. The first fact is spin statistics. Every fermion has spin a half. It's represented not by a space in millions of dimensions, but this spin a half is in a space of 4 dimensions. So every one of those long, skinny
because you put down the particles?
Excuse me? Yeah,
or because you put...
No, 4 because I learned about the Dirac equation in graduate school, and I don't want to think too hard. It's done with 4 component spinners, so even if one goes to Carlo spinners, in the complex theory there are 2 by 2 complex numbers, but I don't have an eye. So I have to make them 4 by 4. It's very hard to distinguish between them and my Arana spinners, which have 4 real components. And remember, I don't really believe this. This is a trial, and I'm ready to drop it and go on to more components as necessary.
There really don't need 8 components?
That's a very good question. And I have a very good answer. I don't know.
That's a perfect answer.
I start with 4. If it doesn't work, 8. I must say 8 has a special attraction. If you have 8 component spinners and 8 component dual spinners, then the vector space is 8-dimensional triality. And people have been looking for some physical meaning for triality for decades. It would be nice if it comes up quasi-naturally, but I don't want to be guided by my ideas of beauty, because I've been misled too often. And now every one of the monadic things begins with a 4-dimensional real part, which I will call the tip. And if you look at the Dirac equation, the proper time derivative of the space-time position is exactly gamma, the 4 Dirac spin operators. So the spin is like a growing tip of the fermion. It tells it which way to go. And each one of these symbols has a 4-dimensional tip, let me call it, which will identify with a 4-component spin tensor. And this completely builds in the spin statistics correlation. Now we have to make a decision about how to represent the unitary charges: hypercharge, isospin, and color. In this gene, after type 2, which is 4-dimensional, comes type 3, which is 16-dimensional, which is just large enough for the spin group and a 12-dimensional expression of gut, which ordinarily is written in SU6 or SO12. And no, it's ordinarily SU5 and SO10. So it might even have room to spare. Okay, so I'll assume that after the tip, which I think of as the head, comes the neck, which is unitary charges. But notice the fundamental difference between all the quantum numbers I mentioned so far and the ones we're coming to next, which are the orbital ones. Every fermion has almost the lowest possible quantum number for the spin or the internal charges. 0, 1, maybe 2, depending on how you count. And all of them have quantum numbers for position and momentum and orbital angular momentum so large that, with the exception of orbital angular momentum, they're often mistaken to be continuous variables, which is obviously silly. So let me use the rest, the body of the symbol for the orbital data. As in the quantization of Yang, which I may illustrate in a moment, the distinction between position and momentum is not as strong in these microquantum theories. And here, I at last bring in what actually was very important to me at the very beginning, not the very beginning, but the near beginning of the program, and that's Penrose's quantization of the CS2 and Feynman's quantization of Minkowski space-time. In both cases, you have a sum of spin operators. And perhaps even more important is a paper I'd probably seen before I spoke of either of them, but it didn't grab me until I was ready for it. And that's a paper of Yang in all this work, both the work of Feynman, Penrose, and Yang on quantum space-time was all done while they were graduate students. And later, Feynman asked me, why do you think I dropped this problem? He worked on it before he worked on the Lamb ship. And I refused to guess. And he explained, because it's too hard. Okay, so here are the Yang commutation relations. And the underlying group is indeed a simple group. Some people here have heard of SO51, perhaps. And the thing is that Yang chose a singular Hilbert space representation following in the footsteps of Snyder, which can be traced all the way back to Heisenberg himself. And one must leave Heisenberg behind. One must take the same group, but treat it as Palev statistics, rather than representing it in interdimensional Hilbert space. And that means replacing these algebraic, this is all going on in L2 of R to the fifth. R to the sixth. And instead, carry out a Feynman type quantization in which the same variables that all these people from Heisenberg to Feynman focused on are represented in a spin representation in the finite dimensional vector space of the same group as the final one. To avoid computing terminology, this really is not the conformal group. The conformal group, I'm speaking now not of abstract groups, but of concrete groups, groups of physical operations. What's usually called a formal group changes the coordinates of a space, but doesn't mix them with the momentum. And this group is abstractly the same, but it mixes position and momentum. So all one...
The same. And the conformal group is so for space. This is that, this is, you are speaking about special linear proof, no? SL51.
No, SO51.
Then
So
you
this is
would have
SL51.
made perhaps
So,
yeah. Then it's the Euclidean, the mark is the Euclidean compartment.
but the physical interpretation is a bit different. And here I'm just emphasizing that the Higgs condensation, or the Higgs field, should not be regarded as the only non-zero vacuum expectation value that we have to account for. I itself has to be obtained as that. And this is a serious problem in my point. So I'll close with some of the conjectures that I've already raised. Maybe the fundamental problem of physics today is the structure of the vacuum. And it seems that there's no immediate impossibility in representing the vacuum as a tight quantum complex. But then the fundamental element doesn't obey Bose statistics. It obeys something, it obeys a Palev statistics. This means drastic changes in the uncertainty principle at high energies. One of the main arguments that both de Broglie and Feynman ran into when they tried to make gauge-ons out of even numbers of fermions is that the Heisenberg uncertainty relation requires these fermions to have enormous energies when they come together to make a photon, say. And there's no sign in the laboratory of the attractive forces that would be necessary to overcome, to bind such high energies. And of course with the Palev statistics, the uncertainty principle is simply wrong. All the components of an angular momentum can be zeroed together. There's no violation of the uncertainty relation. It is just a breakdown of the self-organization of the vacuum that gave rise to I. Thank you.